Today we will discuss about Schrodinger's equation. So before describing the Schrodinger's equation, we should understand what is meant by wave function and its physical meaning. So the quantity with which the quantum mechanics is concerned is the wave function, which is represented by psi of a body. While psi itself has no physical interpretation, the square of its absolute magnitude psi square evaluated at a particular place at a particular time is proportional to the probability of finding the body there at that time. That is, whenever a wave propagating, the quantity which describes the main quantity that which we are dealing with in quantum mechanics is psi, wave function, which is represented by psi, and the psi itself has no physical interpretation, but the square of its absolute magnitude will give you the probability of finding the particle there. That is, whenever a wave propagate, a particle whenever a particle is moving associated with this matter particle, which is known as matter wave. We can locate, or we can find the probability of finding the particle in by the absolute magnitude of this psi function or psi or wave function. So psi square will give you a meaningful interpretation. Energy of the body are other quantities that can be established from the wave function. The problem of quantum mechanics is to determine psi for a body when its freedom of motion, action of external forces. So the wave function is a very important quantity in quantum mechanics, and the problem of quantum mechanics mainly is to determine the wave function for a body when its motion is limited by the action of external force. So this wave function is represented by usually will have both real and imaginary parts. A probability, however, must be a positive real quantity. This means that whenever we predict a probability, means it should be either present or not present. So it should have a value either 0 or 1. Okay, so it cannot be an imaginary quantity. So those psi is represented by a combination of both real and imaginary quantity. Psi square positive real quantity. The probability density psi square for complex psi is therefore taken as the product of psi star and psi of psi and its complex conjugate psi star. So the probability density psi square, so which should be a real quantity, is taken as the product of psi star and psi, where psi star is the complex conjugate of psi. So how do we take the complex conjugate? The complex conjugate can be find out by replacing the imaginary part, that is the imaginary number I, which is square root of minus 1 by minus I, wherever it appears in the function. For example, every complex function psi can be written as written in the form psi is equal to a plus ib, which is a combination of real and imaginary part. So usually wave function appears as a complex function which contains both real and imaginary. This is the imaginary part, this is the real part. Where A and B separately are real functions, but this together means imaginary part. So the complex conjugate of psi means, which is represented by psi star a minus ib. That is, the complex conjugate is obtained by replacing I by minus I. So psi square will give you psi star into psi means a plus ib into a minus ib. A plus ib, you know, a plus b into a minus b is nothing but a square minus b square. So it should be a square minus b square. This I square is minus 1, minus into minus plus, so the result is a square plus b square. So this is a positive real quantity as required. So this will give you, though the wave function psi is a complex quantity, the psi square, which is the probability density, will give you a positive real quantity as we require. So this is about the wave function psi in quantum mechanics. Okay. Now, what is meant by normalization of this wave function? This is an important property of wave function. Since psi square is proportional to the probability density P of finding the body described by psi, the integral of psi square over all space must be finite. That is, the body is somewhere after all. Which means that psi square, the mode value of psi square will give you the probability density, which can be represented by the letter P, probability, in the sense of probability of finding the body described by the wave function psi. So the integral of psi square over all the space will give you the existence of body somewhere in that space. That means if psi square over the space minus infinity infinity is equal to 0, if this integral is 0, which means the particle does not exist. That is, the particle is not existing there. And if this value will give you a result of infinity, still it means nothing. So furthermore, psi square cannot be negative or complex because of the way it is defined. The only possibility left is that the integral be a finite quantity if psi is to describe properly a real body. So it is usually convenient to have psi square be equal to the probability density P of finding the particle described by psi, rather than merely be proportional to P. If psi square is to be equal to P, then it must be true that integral psi square dv is equal to 1. This is known as the normalization condition. So what is described here? So we have already said that psi square will give you the probability density of finding the particle at that time. So if we integrate this psi square over all the space, this value this value should be a finite value. That is, this is equal to 0 means the particle is not existing there. This is equal to infinity will give you no meaning. And if this is negative or complex, then also it will give you no description of the body or no meaningful interpretation. So what does this mean? So it is usually convenient to have this psi square be equal to the probability density of finding the particle which is described by the wave function psi, rather than it is merely proportional to the probability density. So we can written as written this function as minus infinity to infinity psi square dv equal to 1. This is known as the normalization condition. So this is equal to 1 means the particle is definitely existing there. So if a particle is described by a wave function psi, then the particle must be existing there. Then if it is existing there, then this integral must be 1. So this is known as the normalization condition. Since if the particle exists somewhere at all times, we can write integral minus infinity to infinity p dv is equal to 1. That is, this probability density is equal to 1. So psi square can be replaced with this p. So integral p dv is equal to 1. So a wave function obeys the normalization condition is said to be normalized. So any wave function which obeys this normalization condition can be called as normalized. So now we'll discuss about the admissibility conditions for wave function. So the admissibility conditions, besides being normalizable, the wave function psi should satisfy certain conditions. Only those wave functions are admissible for describing a physical system. Wave function should be a finite wave function should be normalized everywhere. This is an important thing about wave function, but it should satisfy some more conditions. Then only it can be admissible, or then only this wave function can be used for describing a physical system. So what are these conditions? These conditions are known as admissibility conditions. So that admissibility conditions for a wave functions are: psi must be continuous and single valued everywhere, since p can have only one value at a particular place and time. Since the probability density can have only one value at a particular place and a particular time, so the psi must be continuous and single valued. And the second condition is that the partial derivatives, that is dou psi by dou x, dou psi by dou y, dou psi by dou z, must be finite, continuous and single valued everywhere. And also since psi must be continuous and single valued everywhere, its partial derivatives also must be continuous and single valued everywhere. And the third condition is nothing but the normalization condition. It should be normalizable, which means that psi must goes to 0 as x tends to plus or minus infinity x, y and z if it is three-dimensional space, in order that integral psi square dv or all space be a finite quantity. That is, beyond the limits, this wave function should be 0, and within the limit it should give you a finite value. So this is the normalization condition, just as we described in the previous part. So these three conditions should be satisfied by a wave function, and these conditions are known as admissibility conditions. Only wave functions with all these properties can yield a physically meaningful results when used in calculations. So much well-behaved wave functions are admissible as mathematical representation of real body. So such a well-behaved wave function, that is wave function satisfying all these admissibility conditions, are admissible as mathematical representations of real bodies. So this is about wave functions. This is an important quantity which describes a physical system and quantum mechanics. So the main problem in quantum mechanics is to find out the wave function which is describing a system. Now, given a normalized and otherwise acceptable wave function psi, the probability that the particle it describes will be found in a certain region is simply the integral of the probability density psi square over that region. Thus, for a particle restricted to move in the x direction, the probability of finding it in between x1 and x2 is given by p x1 x2 integral x1 x2 is equal to psi square dx. Okay, so we have described what is normalization condition, that is the wave function over all the space. If you are integrating, will give you the value 1 or must give you the value 1 if the particle is existing there, or it should be existing there if the wave function is describing the system. So if the particle is restricted to move only between x1 and x2, then the limit should be x1 and x2, then the probability density can be described by this function. Okay, that's all about wave functions. Now we'll discuss about Schrodinger equation. So Schrodinger's equation have two forms. One is time dependent form and another one is time independent form, or otherwise known as steady state form. So first we will discuss about Schrodinger's equation, the time dependent form. So in quantum mechanics, the wave function psi corresponds to the wave variable y of a y motion in general. That is, we usually represents a wave motion, a general wave motion by a variable y. That is, the displacement of the y can be displacement of the wave can be represented by similarly in quantum mechanics the wave function is represented by psi. However, psi, unlike y, is not itself a measurable quantity and may therefore be complex. This is what we have described just before, that is, psi itself is not a measurable quantity, just as we can measure y in a general wave motion. For this reason, we assume that psi for a particle moving freely in the positive x direction is represented by psi, which is equal to a e to the power minus I omega t minus x by v. So what we are doing is, so in a general wave motion, the y, which is the displacement of the wave motion, can be measured. But in quantum mechanics, though psi is equivalent to y of a general wave motion, but it can be measured. So what we are doing is, we assume that psi for a particle moving freely in the positive x direction is specified by this function. Okay, and here omega is 2 pi nu and v is equal to, this is velocity v, which is equal to lambda into nu. So we can substitute for omega here and v as lambda nu. So this function will become psi is equal to a e to the power minus 2 pi nu I into t minus x by lambda nu. And what we are doing here is, we are keeping 2 pi I outside the bracket and the nu is taking inside. So inside it become first term nu t, and this nu and nu will cancel out each other, so x by lambda. This is convenient since we already know that nu and lambda are in terms of the total energy E and momentum P of the particle being described by psi. So it is this form is more convenient to us. So we know the energy of the wave in terms of nu and lambda, so we can describe the system easily. So E is equal to h nu. Since h cross is equal to h by 2 pi, we can represent h nu as 2 pi h cross into nu. So from this we will get E by h cross as 2 pi nu. Similarly, the wavelength, de Broglie wavelength lambda is represented by h by p. Substituting for h as 2 pi h, 2 pi h cross by P. So from this P by H cross will be 2 pi by lambda. So if we are substituting this back into this function, so 2 pi nu is now nothing but E by H cross, and the second term 2 pi by lambda, which is nothing but P by H cross. We are substituting this into this equation, so this will be in the form, and finally we will get psi is equal to A e raised to minus T minus Px. This equation corresponds to the wave equivalent of an unrestricted particle of total energy E and momentum P moving in the positive x direction. So this wave function corresponds to a unrestricted particle, which is very important, an unrestricted particle of energy A and momentum P moving in the plus x direction. This equation is correct only for freely moving particle. That is meant by this unrestricted particle. That is, this represents a wave function corresponding to a freely moving particle which is moving in the plus x direction. However, we are most interested in situation where the motion of the particle is subject to various restrictions, but in real situations the particles may not be free at all times. It may have restrictions for its motion, so we are mostly interested in the motion of the particle which may be subject to various restrictions. So an important concern, for example, is an electron bound to an atom by the electric field of its nucleus. So it's a bound system, and the electron is not free to move at all. It is bound by the potential of this nucleus. So what we must now do is obtain the fundamental differential equation for psi, which we can which we solve for psi in a specific situation. This equation, which is Schrodinger's equation, can be arrived in various ways. So what we are doing is, when we are coming into dealing with a particle which is restricted to move by different situations, we are dealing such a problem in such a way that we will obtain, or we should obtain, a fundamental differential equation for psi. And which can then solve. After that, we will solve for this equation, for psi for some particular situation. And this equation is known as, differential equation is known as Schrodinger's equation, can be derived in many ways, but it cannot be rigorously derived from existing physical principles. The equation represents something new. So this Schrodinger's equation can be derived in many ways, but it cannot be derived from existing physical principles. It represents something new. So we should begin with differentiating equation 3, that is this equation, the wave function equation, twice with respect to x. So if you differentiate, we will give you, that is, differentiating with respect to x means this term can be, the first term can be in the exponential term can be treated as a constant. Only differentiation of this term is valid. And if we are differentiating this twice, we will get, so first differentiation dou psi by dou x will give you ip by minus ip by h cross s, minus and minus sign will give you a positive value, ip by h cross and a to the power minus I by h cross, this quantity. And if you differentiate again, this term will appear again, and the square of this, which will give you minus p square by h cut square, and this function itself, and this is nothing but psi, so we can represent this as minus p square by h cut square into psi. So from this we can write this equation as p square psi as minus h cut square into dou square psi by dou x square. This is marked as equation number 4. And now we differentiate this function with respect to time. So what we will get with respect to time, then the second term in the exponential can be treated as a constant, since in differentiation is with respect to t only. So we will get dou psi by dou ts minus ie by h cross into psi, and e psi is equal to minus h cross by I dou psi by dou t. At speed small compared with that of light, the total energy E of a particle is the sum of its kinetic energy p square by 2m and its potential energy u, where u is in general a function of position x and time. So we can represent E is equal to p square by 2m plus u of xt. So for a particle moving with velocity less than that of light, the total energy can be represented as sum of potential and kinetic energy, and the kinetic energy is nothing but p square by 2m, and the potential energy is a function of position and time. So the total energy is this. Here the function u represents the influence of the rest of the universe on the particle. Of course, only a small part of the universe interacts with the particle to any extent. For instance, in the case of electron in the hydrogen atom, only the electric field of the nucleus must be taken into account. So this u is a function of potential, and this means, or this term represents the influence of this particle, influence of the rest of the universe on this particle. So the rest of the universe means it depends on the situation. It depends on the particular situation. So only a small part of the universe may be come into interaction or come into influencing this. So for example, in the case we are concerned, that is electron in a hydrogen atom, the rest of the universe means, or the influence of the rest of the universe part includes only the electric field of the nucleus on the electron. So if you are multiplying this equation both side by the wave function psi, this equation will become E psi and p square by 2m, here is a psi, p square by 2m psi plus psi u of xt into psi. Okay. Now substitute for E psi and p square psi from our equation. So we have find out what is p square psi by taking the derivative and E psi here. So we are substituting these two terms in this expression here, E psi and p square psi. So what we will get, this equation will take taking the form minus h cross by I dou psi by dou t, which is equal to minus h cut square by 2m dou square psi by dou x square plus u psi, where u is a function of x and t. So we can rearrange so here I is appearing here. So in order to writing it in another form, we can multiply this numerator and denominator by I. So what will happen? This here is 1I and here is I square. I square is minus 1, and this minus minus will cancel, so we'll get I h cross. Okay, since I square is equal to minus 1. And similarly the right side term is remain as such. So this equation is known as the time dependent form of Schrodinger's equation. So here we have dou square psi by dou x square terms only, that is, this is the one-dimensional time dependent Schrodinger's equation. If it is in three-dimensional form, we can represent this equation as IH cross dou psi by dou t is equal to minus h square by 2m into dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus u psi. Okay, this is the three-dimensional time dependent Schrodinger's equation. Time dependent Schrodinger's equation means there is a time factor appearing here because psi is varying with, can be varied with the time t. So a time dependent, this is known as time dependent Schrodinger's equation. And usually this term, which is the del operator, Laplacian operator, which is represented by del square. This is equal to del square. So here is a psi. Okay, psi plus. So this can also be represented as psi h cross dou psi by dou t is equal to minus h cut square by 2m del square psi plus u of I psi. Okay, well, this term is the Laplacian operator del square. So any restrictions that may be present on the particle's motion will affect the potential energy function u. Once u is known as, Schrodinger's equation may be solved for the wave function psi of the particle, from which the probability density psi square may be determined for specified x, y, z and t. So we have already discussed that whenever we are dealing with a particle which are restricted to, we will solve such a problem in such a manner that we should derive a differential equation corresponding to the wave function, and then we will solve for this wave function psi. So this term u represents the influence of this or the restrictions on the particle's motion, and once we know the potential u, we can solve this differential equation for psi, and then we will get psi, and from this we can find out the psi square, which is the probability density of the particle, which can be determined. This is how we are dealing with the wave function in quantum mechanics using this Schrodinger's equation. This is the importance of Schrodinger's equation in quantum mechanics. Okay, so this is about time dependent form. Next we will discuss about time independent or steady state form of Schrodinger's equation.